The purpose of this experiment is to understand the slope deflection method that we talk about in theory of structures. We discussed this method to analyze statically indeterminate beams and frames, and we derived equations which relate the end moments with the slopes and deflections in a flexural member. And this relationship was derived assuming that the structure has to satisfy equilibrium, load deflection relationships, as well as compatibility of displacements. In this experiment, we are going to compare the measured moments with the end moments calculated using the expressions derived in the class. What you are looking at here is a beam connected to these columns which are pinned to the ends, and you can idealize this beam as a fixed beam in which one node is displaced relative to the other node, and that happens when we apply load at that end and this beam is displaced as shown. So one node displaces relative to the other. How much is the displacement for any applied load? We measure that by using this dial gauge. So we measure the displacement of the column to get the rotation of this column, and you can relate the end displacement of the beam with the rotation of the column as shown in your manuals. Once you have the end displacement for the beam, you can calculate the value of the end moment associated with that displacement using the equation in your manual. You compare that analytical moment with the moment you would infer from strain measurements using the strain gauges placed on this beam. How would you do that? You know that strain is related to stress through the modulus of elasticity, and you know the relationship between the stress on the outermost surface and the moment. The expression stress equals moment times y over I, or sigma equals my over I is what you would use to get the measured moments. What you're actually measuring is the strain and then inferring the moment from that strain. So you have the so-called measured moment, and you also can calculate the analytical moment corresponding to a certain deflection and compare these two to try to understand the slope deflection relationship.
This is the setup for experiment number 3, relationship among the end moments, slope and deflection. We have 1 copper plate, 7 strain gauges numbered 1 to 7, 1 weight tray for adding weights, 5 100-gram weights, and 1 TC32K data logger. Knobs numbered 1 to 7 receive data from gauges number 1 to 7. This knob is to be set to 120 ohms. This knob is to be set to 2G. This big knob controls the data from 1 to 7. This displacement transducer must be set vertical against the component. Use a metal ruler to measure all relevant distances and take notes. Attach the weight tray. Set all strain gauges and displacement transducer to 0. Once all gauges are set at 0, check that the displacement transducer is vertical to the component. After everything is set, turn on TC32K. Note the value of each strain gauge by turning the big knob from 1 to 7. The values will appear on the screen of TC32K. Carefully place one 100-gram weight onto the weight tray. Record the strain on the strain gauges by turning the big knob from 1 to 7. Note the value on the displacement transducer. Add another 100-gram weight to the weight tray. Repeat the process. Repeat the process till the total weight on the weight tray is 500 grams. After recording the data, slowly unload the weight tray and remove the displacement transducer.